So let's continue our exploration of thickness changes across a lens. Principally what we want to be able to do is to calculate the edge thickness of a known lens with a given center thickness, or vice versa. So what I've shown here are two meniscus lenses. They both have a convex front surface and a concave back surface, but of course one is a minus lens, a concave lens, and one is a convex lens. But if you look, we can see the relationship between the sag of the front surface and the sag of the back surface, and the edge thickness and the center thickness. So I've labeled those four distances on each of these two lenses, and what you should see is that the front surface sag, S1, plus the edge thickness, TE, is equal to the back surface sag, S2, plus the center thickness, TC. And that relationship applies to both of those lens forms, both the convex and the concave form. So let's write that relationship down, and we can see from this equation now that S1 plus TE equals TC plus S2. And if you don't believe me, just look back at the convex lens again, and that relationship should be very clear. Well, we can do a little algebraic magic with that relationship. First of all, we can rearrange it and get the center thickness minus the edge thickness is just S1 minus S2. So far, so good. We can simplify the left-hand form of the equation, and rather than having that TC minus TE, we can just call it delta T. So delta T, the difference in thickness, is S1 minus S2. Well, we've already derived equations for the sag based on the surface power, the half chord length, and the refractive index, so we can substitute in for S1 and S2 and get this somewhat unwieldy relationship here. But the trick is now to manipulate the right hand portion of that equation and basically multiply the top and the bottom by -1. So we get rid of that annoying minus sign in front of it, and we also convert 1 minus n in the denominator to n minus 1. So that gives us the penultimate line on this particular slide. Well, now we've got two identical denominators, so we can combine the numerators in that equation, and we end up with f1 plus f2 h squared divided by 2000 n minus 1. But of course, f1 plus f2, the sum of the two surface powers, is just the approximate power of the lens. So we end up with this equation that we're going to use several times and keep recycling to explore the relationship between delta T and the lens power, the approximate power, the diameter of the lens, which is actually 2h, and the refractive index. So one thing we should notice about this formula before we go on is that it really ignores the form of the lens. It doesn't independently factor in the base curve or indeed the back surface of the lens. It just uses the approximate power. It's based on the approximate sag formula, and it is an approximate equation. So the other thing we should notice is that since n and h are always going to be positive, the delta T is going to end up with the same sign as the power of the lens. So if we have a plus lens, we're going to end up with a delta T value that is positive. In other words, the center thickness is going to be greater than the edge thickness. Conversely, if we have a minus lens, a concave lens, we will end up with a negative value of delta T. In other words, the edge thickness is greater than the center thickness. But we need to apply a huge dose of common sense, because if we're dealing with a plus lens, we know the center's thicker. If we're dealing with a minus lens, the edge thickness is thicker, and we don't need to get too bogged down with sign conventions and such like. As I've said before, the lens diameter is actually 2h. So h is the half chord length, or half the lens diameter, or to speak more precisely and more generally, it's the distance from the optical center of the lens to the edge of the lens in question. So when we move on to more sophisticated examples where we have a lens that is decentered within a frame, we're going to get more comfortable as using h as the distance from the optical center to the edge of the lens. And finally, just to reiterate, base curve has no impact on this approximate formula. So let's start with an example here. So we've got a round -5 diopter lens. In other words, the optical center coincides with the geometric center of the lens. It's a -5 lens with a refractive index of 1.6, a diameter of 56 millimeters, and a center thickness of 1.5 millimeters. And we want to ask ourselves, what is the edge thickness? So before you go on to the next slide and continue watching this, maybe you could hit pause and apply that newfound formula and figure it out yourself. So I'll be back when you hit play again. Okay, so what you should have done is first of all write down the formula. Delta T equals the approximate power times h squared divided by 2000 n minus 1. And the power, FA, is going to be in diopters, and h is going to be millimeters, and refractive index is obviously unitless. So we plug those numbers into this equation, and what do we get? Well, we get -5 times 28 squared divided by 2000, 1.6 minus 1. And importantly here, we've avoided the trap of just plug in 56 into the equation. We have to divide it by 2, so 56 over 2 is of course 28. And if we plug that into our calculators, we end up with -3.3 millimeters. So in other words here, the value of delta T is -3.3. So we could plug that into an equation, but I prefer to just say, okay, it's a minus lens, so the edge is thicker than the center. How thick's the center? 1.5. What's the difference? 3.3. We add those two together, and we end up with an edge thickness of 4.8 millimeters. All right. That was good. Let's do a plus lens, just so we've accounted for both potential options. So we've got a round +7 lens. So again, it's round. The optical center is at the geometric center of the lens. We've got a refractive index of 1.65, and this time a diameter of 52. The edge thickness, we're told, is 1 millimeter, and we're being asked to find what the center thickness is. So why don't you hit pause and see if you could figure this one out for yourself. Let's go through this example. So we're going to use our tried and trusted formula here, which we use exactly the same as the last example. The center thickness is what we're after, but first we've got to put some numbers into this equation. So the diameter is 52, so that means h is 26. So we'll put in the +7 times 26 squared divided by 2000 times 1.65 minus 1, and our calculators should come up with an answer of +3.6. So this is a plus lens. We've got a plus value for delta T. That means the center thickness is 3.6 millimeters than the edge thickness. The edge thickness is 1 millimeter, and therefore the center thickness is going to be 4.6. We don't need a plus or minus sign, it's a thickness. So far so good. Now let's consider a range of factors that can affect lens thickness. So we've got our previously derived formula, and if you look, there's three factors in there: the power, the diameter, and the index, and we can explore how the value delta t varies as we manipulate each of these variables. So let's first look at the effect of lens power. So our standard diameter here, unless we say otherwise, is going to be 50 millimeters, so a value of h is 25, and our refractive index is 1.5. So our formula is going to predict a linear relationship between delta t, the change in edge thickness between center and edge, and the power of the lens. So here's a nice plot. I've actually shown you I've actually shown you two lines here. I want you to first of all pay attention to the open symbols, the lower, very straight looking line. And you can see that as we increase lens power, delta t increases linearly. So if we have a power of say 10 diopters, delta t is going to be, I don't know, about 6.5 millimeters. So a linear relationship here, and of course if we have no lens power, we have no delta t, so it's implicit that if there's no power, there's no difference in lens thickness between the edge and the center of the lens. So of course, if we think about a 10 diopter lens, if it were a -10, that means that the edge of the lens is going to be about 6 millimeters thicker than the center. And if we have a plus lens, it means that the center is going to be about 6 millimeters or more thicker than the edge. So this is delta t, but we could, this graph applies to both plus and minus lenses. Now what I've also shown you here is a calculation, and we won't go through the mathematics of it, but I've shown the values of delta t for an exactly calculated meniscus lens. So rather than just considering the approximate power, what I've done is go through and assumed a reasonable lens form for a given lens power, and I've calculated exactly the sag for the front surface, the convex surface, and exactly the sag for the back surface, that is the concave surface. And what you can see here, and this is really just the take-home message, is that for low lens powers, the approximate formula that we're going to use time and time again, and we'll probably be asked to apply on a midterm or a final, or both, the approximate power is pretty good, certainly up until we get to powers above 6 diopters. So it's a very useful formula when we're estimating either edge thickness for a minus lens or center thickness for a plus lens. But as you see, when we get to higher lens powers, there's a deviation from the linear approximate line. The exact line increases at a much more rapid rate. We'll see the ramifications of that later on in some other examples. So let's now think about how refractive index impacts lens thickness. So our next graph is going to show how thickness varies with lens power for a 50 millimeter diameter lens, but for 4 different values of refractive index. What you're going to see is that higher values of refractive index result in thinner lenses, and also that the higher the lens power, the greater the benefit of using a higher index material. So let's just look closely at these 4 lines. The top one with a refractive index of 1.5 is just a repeat of the previous graph. that's going to be shown a couple of times for comparison. So if we think about a lens power of about 4 diopters, you see that there's a modest benefit to be gained from taking the patient from a refractive index of 1.5, which would be for a standard resin or CR39 lens, up to something with a refractive index of 1.6 or 1.7. The benefits are much greater, however, when we have patients with refractive errors of 8 and 10 and higher. So here, if we think about a 10 diopter myope, you can see that increase in the refractive index from 1.5 to 1.8 is going to result in a reduction in edge thickness of over 2 millimeters. So basically, the greater the refractive error, the more important it is to consider a high refractive index. The same applies for a hyperope, of course. The benefits are perhaps less tangible, but they're there nonetheless. As we will discover when we think about different lens materials, going to a higher index means a thinner lens, but it doesn't necessarily mean a lighter lens, because the specific gravity or density of the higher index materials tends to be higher. So let's take a look at a couple of graphic examples showing the benefits of moving to a higher index. On the left, we've got a minus lens, and as you can see, when we increase the refractive index from 1.5 to 1.7, there's a dramatic increase, maybe about a 25% decrease, I should say, in edge thickness. The same occurs when we look at a plus lens, except the savings occur for center thickness. Again, if we go from a 1.5 index to a 1.7 index, we get over a 20% reduction in center thickness. So now let's think about what happens when we vary lens diameter or eye size. We're going to look at values of delta T, or difference in lens thickness, for 4 different lens powers. And one thing you'll notice on these next graphs is that the relationship is not linear. That's because delta T is proportional to h squared. So let's have a look at these 4 graphs. And as you would expect, the larger the diameter, the larger the delta T, that is, the thicker the lens will be. So if we look at the first graph down the bottom, you see that for a 2 diopter lens, that value of delta T doesn't really change very much as we increase the eye size from 40 to 60. So there's not too much of a penalty to pay if our patient wants a very large frame size. However, if you think about the 8 diopter myope, or the 8 diopter values shown at the top, you can see that going from a 40 to a 60 millimeter eye size causes an increase in delta T from 3 to about 8 millimeters. So that patient with if they're an 8 diopter myope with a center thickness of 1 millimeter, their edge thickness is going to increase from around about 4 millimeters to almost 9 millimeters. So our high myopic patients are always best encouraged to go for a lower eye size. As I said before, you can see that these lines aren't straight. That's because there is a relationship of a quadratic relationship between delta T and H. These graphs were actually drawn assuming that the optical center is always at the center of the eye wire. In other words, the optical center is in the middle of the frame aperture. In reality, that's not the case, and this next slide, which is borrowed from Wikipedia with the full credit down the bottom, really demonstrates that. When we go from a relatively small eye size, we might have the optical center at the center of the eye wire. And you can see that the distance h from the optical center to the temporal edge of the frame is relatively small. Go into a larger frame size, all of the increase occurs on the temporal side. In other words, the nasal edge of the frame is identically located for both the small and the large eye size. But you can see that the temporal edge of the frame has moved out a considerable distance. In other words, when we increase an eye size by, say, 10 millimeters, h actually increases by 10 millimeters. Now, in the previous graph, we assumed that the increase was 5. So these graphs actually underestimate the penalty that is paid from going to a larger eye size. So we've examined the effects of change in lens power, change in lens diameter, and change in refractive index. Let's now consider base curve, and we can't do that. We can't examine the effect of base curve using that approximate formula. We can plot the graph as the effect of base curve, but as we'll see, it's just a flat line. So the next figure shows the effect of varying the base curve on lens thickness, or delta t, for a 50mm minus 10 diopter lens. The open symbols are based on the approximate formula, and what you'll see is that there's no impact of base curve. It can't factor in the impact of base curve. But the closed symbols clearly demonstrate the effect of base curve. So, as I said before, this is a minus 10 lens, and delta t is plotted as a function of base curve. So the flat horizontal line is the value calculated from the approximate formula. We have nowhere to incorporate base curve into that formula, so the result is that our approximation doesn't vary. But the solid symbols show the dramatic effects of varying base curve. You can see that there's a minimum where there's that red symbol, and that corresponds to a equi-biconcave lens. Now, we wouldn't manufacture a spectacle lens in that form, but it serves its purpose to demonstrate that this actually is the minimum thickness that we could achieve, the minimum edge thickness we could achieve for a lens. So the base curve is minus 5, the back surface is minus 5, given a total power of about minus 10. Look now at the green symbol. That corresponds to when we have a plano concave lens. In other words, the base curve is 0, we've got a flat surface on the front, and the back surface is minus 10. As we increase the base curve, as we steepen the base curve, we can see that the delta t, in other words, the edge thickness, is going to increase dramatically. And certainly once we get above a base curve of plus 2 diopters, we end up with a meteoric increase in delta t, which will translate to a dramatic increase in edge thickness. So what this tells us is that when we're dealing with high prescriptions, there's a premium on keeping the base curve relatively flat. And indeed, in general, steepening the base curve will increase the thickness and the weight of the lens. We can demonstrate this for a convex lens, and even in a modest plus 4 prescription, you can see the effect of going from a plus 4 plano convex lens at the bottom to a meniscus lens with a plus 8 or an 8 diopter base curve at the top. There is a steady increase in center thickness, and the author of this particular diagram has been kind enough to calculate lens weight for us as well. You can see there's an increase in weight. So if you compare the bottom two, the optics, the peripheral optics of a plano convex lens would not be particularly good. So we'd want to go to something that has a slightly steeper base curve. So a +6 would be a good choice in that regard. We might be able to achieve better optics with a +8 base curve as shown at the top, but we're going to observe an increase in thickness and weight by doing so. I want to finish this segment by just demonstrating what happens when we make a poor choice in terms of the blank size for a plus lens. So if we're using stock plus lenses where we only have one blank size available, as we choose a nice small diameter frame for our hyperopic patient, we end up with an ugly edge thickness because we are just edging the lens down to fit the frame. It's much better if we can custom surface these lenses. So either we can resurface the back and reduce the diameter until it's appropriate, or perhaps we could order a custom lens on a digital lathe or a digital surfacing system and make the lens to order. But either way, it's clearly preferable to have a lens where we have minimum edge thickness and therefore minimum center thickness, and the cosmetic appearance and the weight is going to be much better with the option on the right.